Section 1.3. We're going to talk about slope fields and existence of solutions. In many situations, differential equations that you look at are complicated and they're difficult to solve. Sometimes when you have a differential equation, you don't really need to solve it. What you really need to know is, does it have an answer? And if it has an answer, does that answer converge? What do I mean by converge? Anybody know? Approaches a definite finite number as time goes on. That's correct. And a lot of times you can tell if differential equations have solutions, and you can tell if they have solutions that converge by looking at something called slope fields. Anybody know what a slope field is? You might have done a little bit with slope fields in Calc 2. So how do you make a slope field? You do it computer generated. Okay, but how's the computer do it? Magic. All right, so let's say we had a rather simple differential equation, dy dx equals x plus y. That one's really not very complicated. We could solve that one. Well, you can't, but I could. I could solve that one. By next week, you'll be able to solve that one. That one is something called linear, whatever that means. But the way slope fields are generated is generally you make a big table. So you put x's this way, and you put y's this way, and then you have dy dx in the middle. So you might go -2, -1, 0, 1, 2, -2, -1, 0, 1, 2. And you simply plug the numbers in. So this will mean I plug in x equals -2, I plug in y equals -2, I plug it into my differential equation. -2 plus -2 is?
0.
-4. -2 plus -2 is -4. So to start drawing my slope field, I would go to the point -2, -2, which is right there, and I would draw a little piece of line with a slope of -4. So there's my, at the point -2, -2, my little line with a slope of -4. And then I go here. I plug in x is -1, y is -2. -1 plus -2 is -3. So now I go to the point -1, -2, and I draw a little line, but I draw it with slope -3. -3 isn't quite as steep, so it might look something like that. And I would keep going, and I would have to do a whole bunch of calculations. Even this little grid is 25 calculations, 5 by 5. Compute all those numbers, come here and draw all those little lines. And what I would get is I would get something that kind of represents a solution. Okay, so let's take a look at this first one. dy dx equals -y minus sine x. And the idea here is I've given you several initial points. You can kind of see the dots along here. And what I want to do is pick a dot, like this one right here. And if I were to pick that dot right there, what would the solution look like? Well, what has to happen from right here? It comes down, and then it seems to kind of level out a little bit, doesn't it? Till it gets to here, and it goes down again, and then I think it kind of follows right along that curve that's already there. What if I were to pick that initial point down there? It moves upward. Kind of levels off, and then kind of seems to, again, follow along to that curve. And I think this is one, it doesn't really matter where you start. If I were to start down here, it kind of curves up, levels off. You're just kind of following the little dashes there. It's kind of like a game of connect the dashes. Not quite connect the dots, connect the dashes. I think it would look like that. So again, this would be most likely a pretty good thing if this models some sort of real life situation, because it looks like these curves are all converging to the same function. Not sure what happens out here. I'm not sure if the function levels back off or if it continues. My guess would be, because of this trig thing in here, my guess would be that this function would continue to oscillate. If you could see a bigger picture of the window.
Would it oscillate together though, or would it break apart?
My suspicion is that all these solutions would oscillate together.
So how would you find the interval of convergence for the function?
How would you find the interval of convergence? Excellent question. We're not ready to answer that yet. We will be talking about that in the near future. How do you look at a differential equation and know if it has a solution? And then if it does have a solution, how do you know if it's converging to something nice? That's coming up. Good question. All right, let's draw a couple for this other one over here. So, if I'm going to give you a question about slope fields on a test, this is what it's going to look like. I'm going to give you a slope field, and I'm going to give you a couple initial values, and I'm going to ask you to draw the potential solutions. I would not ask you to compute a slope field on a test. Big waste of time. Take way too long. You don't do it by hand, you do it computer generated. All right, so let's say, I don't know, anybody got a point that they like? It's kind of interesting, the solution that's already drawn, isn't it? If you pick this initial point right here, you just get this diagonal line. But what if you pick that initial point over there? Curves down in this direction, then what happens is I go to the left.
It goes parallel.
It seems to come down and kind of be parallel to that line. And how about if I pick that one there?
And also, there's like same shape.
Same basic shape, isn't it? And how about this point over here? Well, from this direction, it looks like it's going just about straight up, isn't it? How about if I go towards the left? Kind of curving down. So it looks like, as x goes towards negative infinity, all of these solutions are converging to that line. But as x goes to positive infinity, we're getting very different things. Depends on which side of the line you start on. Sometimes you get hooks going down to negative infinity. Sometimes they go up to positive infinity. Questions on that? All right, so that's the first thing in this section. A little bit about slope fields. The second thing in this section is existence of solutions. And before we can talk about existence of solutions, we need to talk a little bit about something called partial derivatives. For those of you who have had Calc 3, you know everything you need to know about partial derivatives already. How many of you have not had Calc 3? So we need to talk a little bit about partial derivatives. All right, so what happens in Calc 3? You pretty much redo everything you did in Calc 1, except in Calc 1 your function was always f of x equals something. What do you do in Calc 3? You have functions of multiple variables, so you might have f of xy, you might have f of xyz, 3 variables, 4 variables. So Calc 3 is also quite often called multivariable calculus. So if you have a function of multiple variables like f of x comma y equals x squared plus 2xy cubed minus 5y to the 6th, there are different types of derivatives, and these are called partial derivatives. So quite often we write this symbol, f sub x of x comma y, and that's called the partial derivative with respect to x. What does that mean?
going to derive that equation with respect to x.
And what do you do with y?
It's going to be treated as a constant.
It's going to be treated as a constant. So what this means is you're going to consider this equation back up here. You're going to consider x to be the variable, but you're going to consider y to just be a constant. So if x is a variable, what's the derivative of x squared?
2x.
2x, just like it always was. Plus, if x is a variable but y is a constant, then 2y cubed is all just a number, isn't it? So we've got 2y cubed times x, and the derivative of x is just, so we have 2y cubed because the derivative of x is 1. And the rest is 0, because when we find f sub x, we're considering y to be a constant. So this whole thing is a number. There's no variables in it. The derivative of a number is 0.
For 2x y cubed, wouldn't you use a product rule? Because it's...
Okay, so you're confusing implicit differentiation with partial derivatives. If I'm in Calc 1 and I have an implicitly defined function, then I'm considering both x and y to be variables. And so absolutely I would need the product rule right there. But here I'm not doing implicit differentiation. I'm thinking that this x is a variable and this y right here is just a number.
All right, I see.
So 2x times y cubed is really just x times some number. And so when I take the derivative of x times some number, I get the number. Okay. Conversely, we flip it around. And sometimes we talk about f sub y.
0 plus
0 plus
6xy squared
6xy squared
minus 30y to the fifth.
minus 30y to the fifth. Okay, so now we're thinking y is our variable and x is a constant. So if x is a constant, then x squared is just a number. The derivative of a number is 0. Again, x is a constant, so 2x is a number. So I'm going to have 2x, and I'm going to take the derivative of y cubed. That's 3y squared. Minus, there's no x's there. That one's an easy one. 30y to the fifth. Questions on that? Want to do one more, or you got it? For those of you who haven't had Calc 3 before.
Sorry, I thought it was 6x.
2 times 3 is 6?
So now it's 2x plus 3y.
No, that's a times there.
Oh, okay, sorry.
6xy squared
You split it up.
minus 30y to the fifth. Better? Almost better? Squared? There we go. Okay.
Now, are we allowed to just write it as f sub x and f sub y? If we didn't, Chase?
Yes, quite often if we have like g of x, y is, oh, I don't know, x squared sine y. Quite often we just write g sub x and g sub y, like so. And we'll use those symbols too. What's g sub x? 2x sine y. And what's g sub y? X squared cosine y.
Can we be using x and y as well? Like f sub x, y, or we going that far into it? Or?
All right, so Jesse's question is, we now do things like this. I don't think we will be doing this in this course much, maybe once. I think it shows up in one theorem. What this symbol means is, start with g, first take the derivative with x being the variable, and then take the derivative with y being the variable. So this is like a second derivative, if you will. But you switch your variables, which is kind of interesting. So I do my g sub x, here's my g sub x, and then I take the derivative of that with y being the variable. What's the derivative of 2x sine y? 2x cosine y. And just for fun, what if you switch the order? What if you decide to take the derivative with respect to y first, and then take the derivative with respect to x? you get the same thing. Do you always get the same thing?
No. Well, you should, yeah.
You don't always get the same. Wait, no.
But, yeah, this is like a real property of the.
It depends on the properties of the function. Yeah, there's some continuity issues and some other weird things. All right, so the good news, for those of you who have not taken Calc 3 yet, that's as much Calc 3 as you need to know for this course. You need to know how to take partial derivatives. That's why we allow students to take Calc 2 and jump right to differential equations. You don't need to take Calc 3. All right, so what we're going to use that for today. All right, so we have a function today. You don't really need to write this down in your notebook. This function is given in your book. You can look it up. What this says, this gives us an idea of when we will actually have solutions to differential equations. And so this theorem says, suppose that both functions f and its partial derivative d sub y are continuous on some rectangle R in the xy plane that contains the point a comma b in its interior. Then, for some open interval I containing the point A, the initial value problem, y prime equals f of xy, where a and b, these a and b's came from our initial condition, has one and only one solution that is defined on the interval. So that's one way to tell if a differential equation has an answer. If the original function is continuous, and this is another symbol for the partial derivative with respect to y. So if the original function and its partial derivative with respect to y are both continuous near a point, then you're guaranteed to have exactly one solution. Well, what happens if those things aren't true, though? Well, the theorem is continued, you see. It goes on to say, assume that the original function is continuous, but its derivative is not. If the original function is continuous, but its derivative is not, then you're guaranteed to have at least one solution, but it might not be unique, which means you may have more than one solution. You might have lots and lots of solutions. And finally, if the original function is not continuous and its derivative is not continuous, who knows? There might be answers, there might not be. Those are the hard problems. Those are the ones you don't want to answer. All right, so let's grab a problem or two out of the book here. So the kind of homework problems you're going to have, dy dx equals the square root of x minus y, and our initial condition is y at 2 equals 2. And the question basically is, what does that theorem guarantee you? Does that theorem guarantee you there is a unique solution? Does that theorem guarantee you that there are solutions, but they might not be unique? Or does that theorem guarantee absolutely nothing? All right, so we need to know, first off, is this function, square root of x minus y, continuous near the point 2 comma 2? Near. So we need it to be continuous within some little rectangle containing the point 2 comma 2. Yes or no? Is it continuous in that rectangle?
Yeah.
I hear some reluctant votes for yes. Yeah, it's a little scary to me because I see a square root of 0 there. Is square root of 0 okay?
Yeah.
Yeah, square root of 0 is 0. That's okay. Good with that.
Which one was square root negative numbers?
For example, if I'm at the point x equals 2 and y is just slightly bigger than 2, then what's going to happen?
Imaginary numbers.
I'm going to get imaginary numbers. So am I continuous close to the point 2 comma 2?
Before that. Before, yes. Afterwards. As long as x is less than, as long as x is less than 2, less than or equal to 2.
Well, no, I need to be careful. X can be the number 2 as long as y is not bigger than 2. But remember, they're both variables here. What if x is smaller than 2?
Y isn't bigger than X.
All right, so are we continuous in a rectangle near here? No, yes, no.
She's just picking random points now.
Well, she's right half the time.
Yeah.
No, it's not. No, it's not continuous near the point 2 comma 2 because I get negative values underneath my square root. That's no good. So what does that tell me? For example, if x is 2 and y is 2.00001, then I have 2 minus 2.000. I got a negative number underneath my square root. That's no good. And I can do the same thing if I let x change just a little bit. Of course, I can let y change a little bit at the same time. So if x is like 1.9 and then y is 2, that's again no good. I get negatives under my square root.
So it has to be inside the rectangle. It can't be on an edge.
Correct. We got to be
You could make a rectangle with that in the corner. But
right. This point has to be in the interior of the rectangle.
Yep.
And it can't be in the interior of the rectangle. So this function right here is not continuous near the point 2 comma 2, which tells me, well, no, that's not that 2 comma 2 is not a solution. 2 comma 2 is a point. A solution would be a function. No.
It doesn't exist a function that passes.
It tells me I'm not guaranteed that there's an answer. It doesn't say there is no answer. It says you're not guaranteed that there is an answer. Maybe there is an answer, maybe there isn't. What does it tell us? It tells us we don't know. That's what it tells us.
I know.
It tells us we are not guaranteed any solution. There might be one, there might not be one. We have no way of knowing at this point. All right, how about if I change this just ever so slightly? dy dx equals the square root of x minus y. But now my initial condition is y at 2 equals 0. Is this function continuous in a rectangle surrounding the point 2 comma 0?
Yeah.
Yes, as long as y does not get bigger than 2, as long as y does not get bigger than 2. So this function is continuous near the point 2 comma 0 in a rectangle containing the point 2 comma 0. So if this function is continuous, we then need to check something else. We need to check the derivative. So we now need to know what's d sub y of the square root of x minus y. Well, that's 1/2 times x minus y to the negative 1/2 times the derivative of the inside, which is negative 1. So this original function being continuous guaranteed us that we have an answer. If this derivative is also continuous, that's going to guarantee us that we only have one answer. Is that derivative continuous near the point 2 comma 0?
Yeah.
Yes, because this I don't get 0 on bottom here near 2 comma 0, do I? No, I don't. So the original function was continuous. The derivative is also continuous. That guarantees us
One answer exists.
one unique solution to that problem. One and only one.
Check the
only got, according to that theorem that we had, you only have to check the partial with respect to y. Questions on that?